An alternating voltage source is fundamentally different from a DC voltage source. Whereas a DC voltage source maintains a constant potential difference, the potential difference of an alternating voltage source is always changing with time. And as a result of this, the direction and the magnitude of current in the circuit will change with time as well. There are many ways that the voltage can change with time. We'll examine some of the most common waveforms: a sine wave, triangle wave, and a square pulse. These common mathematical waveforms are often found. The sine wave function will look something like this. The triangle wave looks like this. And a square pulse simply maintains a voltage in one direction, then it will switch to the opposite direction. And it keeps switching back and forth. Now, what does it really mean for the voltage of the source to vary with time? This is a graph of the potential across the source with time. And I'll draw several pictures. Here's our source at time 0, when the phase is equal to 0. Here we'll be at a phase of pi over 2. And we want to see what the source is like at that time. Here we'll have a phase of pi, and let's take a look at the source at that time as well. Finally, we have a phase of 3 pi over 2. And let's see what things are like then. So when we have a voltage of 0, for the source at that time, then there's going to be no potential difference across it. What does that mean for the circuit of just a source and a resistor? It would mean that inside the wire, there would be no field at that time, and no current either. There'd be no reason for charges to move through the wire because it would be like as if there was no battery there at that time. And now let's just say that one end of this circuit is grounded. That means if it's always in contact with the ground, then we know that the voltage is going to be 0 at this point at all times. So when we're at a phase of 0, we've got 0 volts on this side of the source, and we'll have 0 volts on the other side of the source as well. But what about when we get to this peak of the voltage? That could be called V peak or V max. When that happens, we're still going to have 0 volts on this side of the source because it's connected to the ground. But what will happen up here is there will be generated a large positive voltage, V max. Inside the wire, this will cause current to flow clockwise. So there will be a positive field. And there will be a positive current. When we reach a phase of pi, as you can see, we've come back to a voltage of 0 once again. This side of the source will be 0, and the other side will be 0 as well. So see, the one side of our source is always changing with time, according to the graph above. Our wire will return to a field of 0, and the current will be 0 at that time as well. In our last phase, 3 pi over 2, one side of our source will remain at 0 volts, but the other side will now become negative. This has the effect of reversing current and field inside the conducting wire. So if we were to draw the entire circuit, what we would see is no current in this position, we'll get a positive current at pi over 2. Current will return to 0 at a phase of pi. And then when we get to the phase of 3 pi over 2, interestingly, the current reverses direction. This is an oscillating or alternating current, constantly switching back and forth in its direction. The type of function we have will affect the brightness of any bulb that's involved. Let's say that all of these waveforms have the same peak voltage. What if we were to, one at a time, connect all of these sources to a single 25 ohm bulb? Would we be able to tell the difference between the sources just by looking at the bulb? The answer is we will be able to tell the difference. And even though they all have the same peak voltage, they will not have the same what is called RMS voltage. RMS stands for root mean square. It's a statistical measure, a sort of average value of the voltage that can be calculated using statistical methods. And one of these graphs has a higher VRMS than all the others. The RMS root mean square value is based on what percent of the time do you hold a large voltage value. Like which of these sources would cause the most current to flow on average, and which one would cause the most power to be dissipated in the bulb with time. Take a guess for yourself and see if you can decide which one has the largest root mean square value. Well, we can draw the root mean square value with a dashed line in the graphs. And the one that has the largest is actually the square pulse. The reason why is because it holds a large value of voltage for a longer time than all the others. See here in the triangle, the voltage spends just as much time around a value of 0 as it does at the peaks and valleys. When it comes to the sine wave, the graph actually spends more time at high values than it does at 0 values. The area under the curve has a lot to do with this. We can actually rectify it, which means make it just positive, and then we can draw the RMS value. So if we neglect the direction of it, then the RMS value here for a square pulse just simply equals the peak value. So interestingly, if you hook up a square oscillator to a bulb and let the frequency of it be really high, then the eye can't tell the difference between a square pulse and a direct current with that same value that the blue line has. When it comes to these other guys, their RMS voltage is less than the peak value. Now you might be tempted to think that the square wave, you think that the VRMS might be half the peak value. But because this is a root mean square technique, a statistical technique, it's not exactly an average value. It's just a little bit different. It turns out to be the peak divided by the square root of 3, which is approximately 0.577. Of the peak value. All right, so we want to go right about here. So if we were to use a direct current with 0.577 of that peak value, then to the naked eye, as long as the frequency is high enough, you wouldn't be able to tell the difference between that DC value and this triangle wave. For a sine wave, the formula is V peak over the square root of 2. Which turns out to be approximately 0.707 times the V peak. So this one will be larger. Than the triangle wave. The larger the RMS value, the brighter the bulb will be. So let's rank these sources in terms of how bright of a bulb they would create. As long as the frequency is fast enough, our eye won't be able to tell that the current is alternating. And when it comes to the power delivered to a home, frequency of oscillation is approximately 60 hertz. And so apparently this is a fast enough oscillation that if you look at a light bulb, you can't even hardly tell that the current is changing direction 60 times a second. It's too fast for the eye to even perceive. But if we record a light bulb with a high-speed camera and slow down the frames, you can actually see this effect happening. But anyway, if we were to look at these different bulbs, let's rank them according to brightness. So the square pulse hooked up to a light bulb will create the brightest situation. When it comes to the triangle and the sine though, the triangle would be the dimmest, and the sine wave would be in the middle.